Okay, hello and welcome back. So in today's video, we're going to continue our lessons on computing volumes of solids of revolution. And once again, we're going to learn a new method. So we've learned the disk method, we've learned the washer method. Today, it's time for the shell method. Fair disclosure before we begin, some people find the shell method to be the most challenging just because the disk and washer were so similar. So don't be afraid if this takes some time to conceptualize, but being able to conceptualize what's going on will take you a long ways because it'll help you solve these problems a lot quicker. With that said, I'm going to do my best to explain it well before we get into some problems, give you some diagrams that will hopefully solidify that if you're a visual learner, though I'm not a very good artist. And yeah, feel free to leave questions in the comments below, and let's get into it. So let's take a moment to understand the shell method. So this is yet another method to determine the volume of solids obtained by rotation. And the shell method uses cylindrical shells to evaluate volumes. So yeah, we're going to be dealing with cylinders a lot here. And this method is particularly useful when a variable cannot easily be isolated in a function. So remember, sometimes when we have like a vertical line of rotation, we have to change our equation such that we solve for x in terms of y, because the integral is with respect to y. Sometimes we'll have functions such as the one given here, y equals x cubed plus 3x squared minus 2x, and if we were to revolve that about a vertical line, we would have to solve for x if we wanted to use like the disk method or the washer method. But solving for x here in terms of y is not very easy to do whatsoever. So in these instances, we're going to have to use the shell method. And the main equation we'll be taking advantage of here is the area of a cylinder, 2 pi RH. So this is the lateral surface area of a cylinder that we'll be using, 2 pi RH. If you take a moment to think about this formula right here, this breaks apart into 2 pi r times h, where 2 pi r is the circumference of a circle. And that kind of makes sense, right? If we were to draw a cylinder here, what we're doing is we're taking the bottom, like the circumference of this circle here, and then that extends upwards for a total height of h. So I think I mentioned this in my disk video, or maybe it was the volumes by cross sections, where we're adding volumes and you can think of it as stacks of paper. Same thing here, where for surface area, we just trace one circle, then trace the circle right above it, and keep on doing that until we reach the height of h. That's the equation. So it's good to understand that. R is the radius perpendicular to the axis of rotation, so that'll make some sense once we get into some of the problems. H is the height or length of the cylinder, so we can use those terms interchangeably. And why are we using the area? Well, 2 pi r gives us the circumference of the shell, and then we multiply it by an infinitesimally small height value, which will give us the volume of the shell. So this is exactly what I explained over here. 2 pi r for the circumference, and if we're finding the volume of a very thin cylinder, we just multiply it by that very thin height, which will give us a volume. So I'm going to show this video now. I have to switch screens, but what's going to happen is the region we're revolving is the pink region, and that's going to be revolved around the y-axis. So you can kind of try to visualize what that final solid will look like. It'll be like a bowl of sorts. And what the video will show is what the shells we're creating actually look like, and what shells we're finding the volume of. So let's switch to this screen. Okay, here we go. So we can see that there are 3 shells being drawn now. Right now they're half cylinders only, but in the second part of this video, it'll complete the shell. And we can see here now that the cylinders are being completed. And as we combine all of these cylinders together, we can roughly get the shape of what that pink region would be if it were revolved around the y-axis. Now, you'll note that these cylinders, like the rectangles that are being revolved around, they're very wide. When we do this with calculus, these are going to have infinitesimally small thicknesses. So, yeah, that's how we get the volume using the 2 pi RH thing. So this is the idea of the shell method, where we're constructing outwards using cylinders. With disk method, we kind of stacked disks on top of each other. Shells are building outwards. Maybe think of it as like the nesting dolls or something like that, how the cylinders are nested inside of each other. So this is the visualization. I'll let this play one time through, but note how when the cylindrical shells are completed and all put together, we get the final solid that we're looking for. And we have to find the volumes of each of these shells. Okay, let's do it. So these are the formula we'll be using. When we have a horizontal axis of revolution, the volume will be 2 pi, then the integral from a to b of r of y times h of y. I should actually change the limits to be c to d, like that, because that's what's shown in the picture. The picture might be a little bit confusing right now, and I'm not a big fan of the picture, so I'll explain it in a moment. But when we look at the vertical axis of revolution, it's nearly the same thing, except the integrand is r of x times h of x dx. So notice the difference between this and the disk method. Besides the disk method being pi r squared, here, when we have a horizontal axis of revolution, we integrate with respect to y. And when we have a vertical axis of revolution, we integrate with respect to x. So if we think back to the video we just saw, notice how the cylinders were building outwards to the sides. So the x was changing and we were getting more shells. It wasn't changing as we went upwards necessarily. And so what's going on here is that now, in the case if we scroll back, this equation here, if we were revolving it around a vertical axis of rotation, we had to worry about solving for x, but now we don't have to worry about that because the integral is with respect to x. So this changes things a lot, and with this we'll have a lot more freedom with how we compute these volumes. So here is another drawing that I drew. It's not great, but I'm going to try my best to explain what's going on here. So imagine this function here, which we're revolving around the x-axis, and the resulting shape will, I don't know, look something like this black shape here. It's like a sideways bell of some sorts. And so an example of one of the shells that we'll be finding is the pink cylindrical shell that I just drew. And remember, we're computing the volume of this. And the way it's going to work is that this is the radius here. This is the height of the cylinder, and it has a very thin thickness. So the volume will be given by 2 pi RH times dy. And what we're going to do is we're just going to sum up a bunch of these cylinders, which is essentially taking the integral of all of them, right? So this equation here comes from that 2 pi r times the h to get the lateral surface area, and then multiplying it by a very small amount because it has a very small thickness. But why does the thickness look like this? Well, let's take a look at another shell, this blue shell here. It has a different height now and a different radius, but it'll have the same thickness. And we can have many of these shells, but when we put them together, it'll look something like this. We have this pink shell here, and then right within that is this blue shell, and then within that is another shell, this red one, and you can see that we can continuously build them up until we get to like a very, narrow shell right here, or a very wide shell at the bottom here. But as we build them up, we get to the shape of this bell. So that's the idea of what's going on. The disk method would be a little bit different. I'm going to try to explain that right here. So it's not a great drawing, but let me try to fix this actually. So that's sort of the shape. The disk method would take this disk, which has a very small height to it, and then add on this disk, and then add on this disk, and so on, and upwards. Here, these are, so they're being stacked on top of each other. With the shell method, they're nested inside of each other. So that's a lot of explanation, but hopefully you're beginning to visualize what's going on. And with that, we're going to try to solve some problems. Yeah, let's get into it. So find the volume of the solid formed by revolving the region bounded by y equals x minus x cubed, the x-axis, the y-axis, and x equals 1 about the y-axis. Okay, so this is a vertical axis of rotation. Okay, first I like to draw the graph just to see what it looks like. What is the graph of x minus x cubed? Well, maybe you don't know it off the top of your head. So why don't we revisit a topic we learned about quite a while ago, curve sketching. Here we go. This is exactly what we want to do. Let me draw a set of coordinate axes right here. So our function is y equals x minus x cubed, which we can say is equal to x times 1 minus x squared. 1 minus x squared is the difference of squares, so we can factor that out into x times 1 plus x times 1 minus x. So that tells us that there are zeros at x equals 0, -1, and 1. Those are the values that make the function equal to 0. Cool, so let's try to mark those on the graph here. I'll just put dots where it intersects the x-axis. Now, we know it's a cubic function, so we know the general shape of a cubic function. We just need to think about like what it actually looks like. And for that, we can take the derivative of the function to get some critical points. We can also take the second derivative to learn about concavity, things like that. And from there, we'll have a good idea of what the curve looks like. So let's take the derivative of this. Y prime equals 1 minus 3x squared. To get the critical points, we set that equal to 0 and solve for x. So solving for x, we get x squared equals 1/3, or x is equal to 1 divided by the square root of 3, plus or minus. Okay, so we have two critical points. Let's take the second derivative. So that's going to be equal to minus 6x, and okay, and then from there, we know where the concavity changes by setting this equal to 0. So this gives us x equals 0 as our point of inflection. From here, we can draw a sine line. So we'll put 0, and we'll put our critical points as well. So this will be 1 divided by the square root of 3. This will be 1 divided by the square root of 3 minus that. Okay, so with that in mind, let's see, what do we have here to work with? We can get an idea of the slope of the tangent line at certain points. So what is 1 divided by the square root of 3? The square root of 1/3. So there's a couple of ways of thinking about this. This is actually kind of challenging. So the square root of 3 is less than 2 because 2 squared is 2 squared is 4. 2 squared is 4. So 1 divided by the square root of 3 is going to be greater than 1/2, right? And then we also know that 1 divided by the square root of 3 is less than 1. So we already have some idea of what values we can test. So let's test the far right with x equals, we can try x equals 1 here. So the first derivative, f prime of 1, I'll just call y prime f prime. So f prime of 1 is equal to 1 minus 3 times 1 squared, which is equal to negative 2. That's less than 0. So the slope of the tangent line is negative. In between 0 and 1 over square root of 3, we can test x equals 1/2. F prime of 1/2 equals 1 minus 3 times 1/2 squared, which is equal to 1 minus 3 times 1/4. That's greater than 0. So that's going to be a positive tangent line there. Here we'll try x equals negative 1/2, and if you compute the first derivative at negative 1/2, you'll get the same thing as we just did. That's greater than 0, so it's a positive tangent line there. And then finally x equals negative 1, f prime of negative 1 equals, let's see, 1 minus 3 times negative 1 squared equals negative 2, less than 0. Okay, and then as far as concavity goes, we can test like f double prime of negative 1 on the left-hand side, because the only point of inflection is 0, so that's going to be equal to negative 6, which is less than 0, so that's concave down. And then f double prime of 1 is equal to negative 6, sorry, this is positive 6 here, whoops. I can probably edit this out. So now for concavity, we can test a point to the left and to the right of 0, since that's the only point of inflection. So on the left, we'll do f double prime of negative 1, which is equal to negative 6 times negative 1, which is 6 greater than 0, so it's concave up. And on the right, we can test f double prime of 1, which is equal to negative 6 times 1. That's negative 6 less than 0, concave down. So now we can zoom in here and sketch our function. So it starts out by having a negative tangent line, and then it continues with that until we reach x equals negative 1 over root 3, which is somewhere here. We'll just call it like here. And then on the other side, we have 1 over the square root of 3, which is somewhere here. So we continue downwards, and then we change to having a positive tangent line. Remember, we're concave up. Whoops. We're concave up. And then we continue, we hit 0. We're still going positive because it has a positive tangent line. But now we have to switch to being concave down. And then at this dotted line, we switch our slope and then continue downwards. So this is roughly the graph, what it looks like. So a nice little review of what of curve sketching. So I'm going to erase all of this and then only draw the first quadrant because that's where our lines bound the curve. So let's highlight all of this and delete it. So we zoom in here and then draw our first quadrant. And our graph in the first quadrant looks something like this, where this is 0, this is 1. We're bounded by the x-axis, the y-axis, and x equals 1. So indeed, this is the region right here that we're revolving about the y-axis. Okay, so what does this look like when it's actually revolved? I drew some sketches and hopefully they're good enough, so let's reveal them now. So this is sort of what it looks like when it's revolved around the y-axis. So you can think of it as like a couple of things. It's like a donut, but its hole doesn't go through, it like stops. You can think about it as like a bundt cake, kind of. Another thing is like it's like a parachute, you know, in like young schooling when everyone has the parachute and then they lift it up and then they go underneath and sit on it and it creates this dome. Imagine that dome, but there's something on top of the dome in the middle that makes it touch the ground. That kind of shape. That's what's going on here. So that's the drawing on the left. On the right is a demonstration of the cylindrical shell that we'll be computing the volume of. It's only one of them. I was scared to draw more because I would mess up the drawing more than I already did. But the shells will grow outwards. Remember, it's a vertical axis of rotation, and so that means we're going to be integrating with respect to x. Why are we using the shell method? Well, if you try to solve y equals x minus x cubed, with the other methods, being the disk method and the washer method, you would have to solve for x in terms of y here. So let's try that. We can try factoring out an x, 1 minus x squared, or even further. But now what? Like, how do I solve for x in terms of y? I can't do it. So for that, we need the shell method. So remember, we're going to be now integrating with respect to x. So let's pull up the equation and try fiddling around with it. V equals 2 pi integral from a to b r of x times h of x times dx. So let's try to figure out what exactly is going on here. We're integrating with respect to x, so each little chunk of x, each tiny bit of x, is going to give its own rectangle. So we can draw like a rectangle there. And you can imagine if that whirls around the y-axis, it'll create a shell, something like that. The colors don't match, but oh well. So that's what we're going with. That's the idea of what we're going with here. But in our integral, we have r of x and h of x. What is r of x and what is h of x? You could refer back to the drawing on the previous slides, but I would like to actually take a moment to think about it. So if this blue rectangle being spun around the y-axis yields this shell, how would we find the volume of this shell? Well, we're going to be using that 2 pi r h or whatever, but the radius is this right here, which seems to be the distance from this like sink point to the edge of the rectangle, right? So an analogy here would be this distance here, because we know 0 will be the sink point. So our idea is that this distance is r of x, which means that this vertical distance is h of x. And now you can think like, when I spin that around, yeah, that makes sense. That'll give a height h and a radius however far we are away. Now remember, these are functions of x, so let's try to find them. R of x should be pretty simple, right? Considering our sink point is at 0, our axis of revolution is at 0, it's the y-axis. R of x is the distance from our rectangle to that axis of rotation, which in this case is just going to be x. Okay. H of x, well, in this case, when we're here at this point x, our h of x is going to be whatever value we're at on the function, which is f of x. So h of x equals f of x. F of x is x minus x cubed. So with that, we can compute the volume now. We have v equals 2 pi integral, we'll get to the limits in just a moment. The radius is x times, height is x minus x cubed dx. The limits now we'll think about, we're integrating with respect to x. The rectangles start to be built at 0, and they continue all the way until we reach x equals 1. So those will be our limits here. Now we just have to solve this integral. So let's do that. V equals 2 pi integral 0 to 1 x squared minus x to the 4th dx. That's 2 pi times 1/3 x cubed minus 1/5 x to the 5th, evaluated from 1 down to 0. That's 2 pi times 1/3 minus 1/5, or 2 pi times 2 over 15, which is equal to 4 pi over 15. And that's our answer. See how simple this was now? If we were doing the disk method or the washer method, we'd be here for ages because we would have to solve for x. With the shell method, It greatly reduces the amount of work we have to do. It just takes some time to conceptualize what's going on here. So that's the idea of the shell method. We'll do one more problem. Find the volume of the solid formed by revolving the region bounded by x equals e to the negative y squared, the x-axis, the y-axis, and y equals 1 about the x-axis. I won't make us try to graph this curve again because we've just exercised our ability to do curve sketching. Although this one might be a little complex, so maybe you would need a graphing calculator or something like that. But I'll just give it. I just like this equation because of the integral it produces, but you'll see in just a moment. So the graph that we're dealing with is going to look something like this. I'll draw the first quadrant. Note that one of the lines we're constrained by is y equals 1. So I'll draw that in red here. Yeah, so the graph of y equals negative y squared looks something like this. So when we draw the actual region being bounded, it's this green area here. So I'll just highlight the actual bounds of the region in black. So this is the region we're dealing with here. And we're revolving this about the x-axis, which is a horizontal axis of rotation. So what does this look like when we revolve it around the x-axis? Well, I'll show that in just a moment. For now, let's think about what method will be used to solve this. Well, if we were using the disk method or the washer method, we would have to solve for y. So that would give us, let's try doing that. So we have ln of x equals negative y squared, and then that means y squared is equal to ln of 1 over x, and then y equals the square root of ln of 1 over x plus or minus. Maybe you can do something with that, but that just seems a little bit nasty to me, and since we're talking about the shell method, why don't we do it? So we're thinking of using the shell method, and that'll be nice because we already have this here. Okay, so that means we're going to be solving for x in terms of y or whatever. It's with respect to y now, our integral. Okay. So here we revolved it around the y-axis. We got this shape here. Now we have this. So this is a sketch I did a while back. And that's what's going on here. So there's a shell drawn with it as well, but I'll try to highlight the actual shape in red here. So it's going to be this right here. And you can think about it as like a cupcake or something, I don't know. And then in pink, I'll draw the shell of what's going on. Something like this. It's kind of hard to make it out because, yeah, so that's kind of the shell that's going on. You can see it's a cylinder with some thickness here. So this is our thickness. And then this is our height here. And then our radius is to this axis here. The shell, the x-axis goes through it because we're revolving it around the x-axis. So this is our radius. The diagram maybe doesn't make it seem like that, but I assure you it is. So that's the overall shape that we're dealing with here. Okay, so let's try to compute the volume of it. I'll go here. So V is going to equal, let's see, we're doing a horizontal axis of rotation. So if we go back here, we have this equation. So V equals 2 pi integral c to d r of y times h of y times dy. Right? Something like that. So we have 2 pi. Let's try to find the radius and the height. So since we're integrating with respect to y, we want to think about the radius in terms of y. Well, here, the radius is just going to be whatever value of y we're at, because the other part of the shell will be at negative y. Remember, it's symmetric around that line 0. So radius is going to be equal to y, just like before. The height, let's zoom in here and draw a rectangle. The height of this rectangle is the x value of wherever we are along the function. So given a value of y, we need to find its corresponding x value such that it's on the function here. And that would be given by our function here, because we've already solved for x. So h of y is going to be equal to e to the negative y squared. So coming back to our integral, we have 2 pi. Integral goes from 0 to 1 because these rectangles start stacking at 0, and they go all the way up till 1 because this red line is the line y equals 1. R of y was y. H of y was e to the negative y squared. We have dy here. Let's solve this integral. For this, we can use some u substitution. U equals negative y squared. Du equals negative 2y dy. This integral simplifies to 2 pi 0 to 1 y times e to the u times du over negative 2y. We can cancel out a y here, we can cancel out a 2 here, we get negative pi 0 to 1 e to the u du. Integral of e to the u is e to the u. So this is negative pi e to the u, which is equal to negative pi e to the negative y squared, evaluated from 1 down to 0, which is equal to negative pi times e to the negative 1 minus e to the 0. That is equal to negative pi times 1 over e minus 1, or pi times 1 minus 1 over e. And that is our volume. So just like that, we've used the shell method, this time revolving it around the x-axis. Again, maybe it's a little bit more conceptually difficult, but I like to think about as really these are acting as shells. When you crack open one shell, there's another shell within it, or the nesting dolls, that they keep on expanding upon each other, and together they can construct the overall figure. So these are particularly helpful when solving for one variable is challenging, and that's when we use the shell method. So that concludes our series of different methods on computing volumes. In the next video, we'll take a look at arc length and surface area, so get excited for that. But yeah, thanks for watching, and as always, take care.